Bismillahirrahmanirrahim. Today, I'm here again to discuss another most versatile paper in the era of artificial intelligence and computer vision. This paper is basically a foundation model, a foundation paper that support the medical image processing and diagnosis and open the door for future researchers to invest their work in this domain. And it is one of the most versatile paper, and let's deep dive into it, and let's see the title of the paper. So the title of paper is PLIP, a visual language foundation model for pathology images analysis using medical data. So recently I have uploaded another research paper digest that is related to CLIP, which is also a visual language foundation model for natural images. And that this paper is also inspired from CLIP. But this paper addressed the issue for medical diagnosis using pathological images. So let's see the major contribution of the authors and how this paper is very effective in the domain of medical diagnosis. So the title of paper is Visual Language Foundation Model for Pathology Image Analysis using Medical Twitter. So if we see, the pathology is medicine's ground truth. And how can I say that? Is whenever a person is being diagnosed with any kind of abnormality, so what happened that patient observes some symptom that appear in the autonomy or either the physical form or the internal body parts, and these symptoms will further help the doctors to find out the clinical sign that help them to diagnose and predict the possible disease. Then, to support these their decision, the physician will ask the radiologist to check the radiological profile for the patients and to look at the abnormalities and the possible presence of any anomalies in the body part. It might be a cancer using some radiological images like CT scan, MRI. So these images will help the doctor to say that the cancer is present in the this organ in that region in that location. To further strengthen their study, they ask pathologists to do the biopsy part and to see whether the cancer is benign or malignant. So these are the basic steps that are being followed in diagnosis of cancer. And then when it is showed by the pathologist that this disease or this cancer is benign or malignant, then based on those decisions, treatment plan is being suggested by the doctors or surgeons. So that is how the basic flow of work. So what is the problem we are facing right now is that lack of availability of pathological data for training the model for artificial intelligence or for deep learning models. In case of radiology, there are some kind of data that is available online, which is annotated, but for pathology, we hardly find some credible data repository that support the establishment of these uh, these models that help in automated diagnosis of disease. So clinicians need consensus. So uh, although there are not availability of any kind of data set present online, but what doctors are doing right now is that they use some reference book material in which they ask certain questions like pathologists, do we always test Ki-67 in breast kinemos? So these are the questions that are being asked by the doctors, and they are using social media path Twitter to collaborate with one another in um, coming up with certain conclusion or deciding about the medication. So doctors are using the Twitter or social media sites to collaborate with one another for certain decisions. And similarly, there are some positive feedback that is being appeared for this query, and there are some negative feedback which also appear from one of the hospital of the Spain. So that is how doctors are learning through different cases by collaborating with one another. So pathologists, do clinicians make diagnosis based on subjective gut feeling? Like if they haven't seen that case previously, so it's also difficult for the doctors to come up with conclusion and to suggest the medication and identify how the prognosis of this disease will occur. So pathologists also need some uh, subjective measure to understand how the things will move. So mostly this survey is being conducted, and it was appeared that mostly people or surgeons do 40% of in cases in which they haven't seen that before, so they take random decision based on their past experience. So that is how people are working in the domain of medical diagnosis. So when we are comparing cases with classic cases, it's very difficult to have a bulk of data and then identify that these biomarkers are similar to biomarkers of these cases. So, but we can also see that these stained images are also available by surgeons or pathologists on their tutor handles. So a visual language foundation model for pathology image analysis using medical Twitter. So the main objective of this author is to provide some foundation for computational pathology. And the major objective of the author is to overcome all the challenges that may appear in construction of the data set, uh, having a comprehensive data set with their proper text annotation to describe all the cases of pathology. And as pathology support more than 8,000 disease types, so it will be crucial to have some kind of data set that have all the samples of these 8,000 diseases type. So there is a solution like social media sites like Twitter have their hashtags along with text label and image samples of various cases. And people also replied on those cases and suggested the way forward for it. So this will be a quick start to use this data and avail it for diagnosis using pathology images. So authors have used and construct open path dataset, and what they did is they used Twitter API, which is free for the educational purpose at the time before Elon Musk have joined. So they have compiled a data from 2006 to 2022, and they use these hashtags of which are of 32 type of hashtags, and they have extracted the pathology images along with their captions as a label, and along with the reply or the response of other authors on these sample text. So they have used these hashtags, and all the data were in English, which are annotated in English, and they have disabled not to retweet to further clean the data, and they have not used any kind of sensitive data. So there are certain flags that are present on a Tutor API in which one of the flag is sensitive or not. So they have enabled it that data should be non-sensitive and reply with more like. So this will validate that the data is almost correct because majority of pathologists have reply on it, and they have also applied some text cleaning and some stamp stop words removes, and then they have applied some NLP pre-processing techniques to further refine the text. And then after that they obtain images with their text, and then they remove the non-pathology image using a classifier that was based on binary, and that classifier will help them to recognize that this image is a binary, this image is pathological image, or this is not a pathology image, or that is just a normal image. So they have used a classifier, and after obtaining 98% accuracy in correctly predicting the pathology image, they further personally evaluated to check that the images obtained are correct and there is um, no misclassified data that is present in it. So that is how they have compiled entire data set, and that was basically the support of US Canada Association of Pathology in 2016. So they have used this project under the sponsorship of this project. They have developed this data set. So what they have obtained by extracting or scrapping the data from Twitter and other social media sites, that they have obtained 208,414 high quality image text pairs, and which is considered as one of the largest public pathological visual language data set. And for each hashtag they have obtained 598 tweets and 343 replies. So see how much data they have collected from Twitter along with their pathology images. So with 32 different hashtag neuropath, and the length of text should be 20 words. So not more than 20 words they have obtained on the dataset. So if we see the average calculation for all dataset is that the number of words to represent them is 17 words, and replies were approximately 15, tweets were 20. So small infiltration look gang with calextroid excretion are suspicious for prostatic endocrine. So that is how they have obtained the text and pathological image along with it by curing with Twitter. So if we uh, understand the entire paper and the major contribution of their work, there are two prime contribution of this work is that they have performed image classification. So PLIP is a multimodular AI model that combine both images and text for understanding. They have used vision transformer and PERT, and it is trained on open path dataset. So how PLIP can work. So it work on two tasks, mainly two tasks, that is image classification task. PLIP achieves state-of-the-art zero-shot and transfer learning performance for classifying new pathology image across diverse data sets. So it is capable to classify images using transfer learning and zero-shot learning. Zero-shot mean if there is no class, the class is not present in the data set, still the model is capable to segregate it from rest of the classes. So that is the capability of zero shot. and it also have the capability to perform a retrieval task for image to image and text to image retrieval. So user can retrieve similar cases either using images or natural language search, making a knowledge sharing easier. So another contribution is PLIP extract visual language feature from pathology image and their corresponding text description. So they have compiled a large data set that is OpenPath, and its fine-tuned version is basically it is the fine-tuned version of original CLIP model. So it has as CLIP, we already discussed about CLIP model. So it has all the property that is present in CLIP, like it supports zero-shot learning, transfer learning, text-to-image retrieval, and image-to-image retrieval. And here we have some description about the dataset. That OpenPath dataset consists of 208,414 pathology images paired with natural language description. It is currently the largest public dataset for pathology image annotated with text. So that is the major contribution. And we will further describe about this model later in the slide. So here they have used this data set, that OpenPath. And if we see that uh, OpenPath data set can be further described, that there are 116,504 posts and 59,869 valid replies. So they have used this data set, and Path9 data set was 32,000. So they are just showing the diversity of their data set as compared to a state-of-the-art data set for pathology. So what they did is they used this OpenPath data set, a high quality image text pair, extract the use the PERT model to extract the text embedding and text encoded and get the text embedding, and then image encoder to get image embedding, and then they find their dot product and find their cosine similarity. So the diagonal matrix will have the maximum value of the similarity. Like if I have a text that is representing the class 1 and the class 1, the text for class 1, so they both have the higher value in when their dot product is being computed or their cosine similarity is being computed. For next class, like uh, the pathology image and text for the next class, its cosine similarity will be lower as compared to their own class. So that is how they have computed for entire uh, classes, and the maximum value is obtained on the diagonal value. So they perform some training for certain number of steps to get the most optimal value. So these are the texts which was extracted from the Twitter API along with its pathology samples. Text is being passed to text encoder, image is passed to image encoder. It will form a dot product and cosine similarity is being computed. So that is how it will going to work in contrastive fashion. And the loss for this model is contrastive loss, which is opposite of cosine similarity. So what contrastive loss will do, it will maximize the similarity between the same class of image and text, and uh, maximize the similarity and increase the dissimilarity between the opposite classes. So that is how the contrastive loss will work in this way. So this is the working of PLIP. How it is different than CLIP? It's based on pathology image and text obtained from the books and Twitter or social media website to give the label to these pathology cases. So PLIP can classify new images without further training. So this is the quality of PLIP that we already have studied, that it has the capability of zero shot learning. Zero shot means if the class is not present in the training set or support set, still the model has the capability to segregate it from rest of the classes and not place it in the wrong class. So that is the capability of zero shot learning. So it can, firstly, the model is being trained on all the classes that is available in the data set for the pathology image. If a case appear in which is not belong to any of the class, then the model will place it into a new class and label it that this class is not belong to any of it. So that is the capability of PLIP. PLIP. So apply model to new tasks immediately, rare or novel disease identification. So it will help in diagnosis of rare and novel diseases. So PLIP can classify new images without further training. So we already discussed that it has the capability of zero shot learning. So they have used not only the open path, but they have used other data sets for cross evaluation. They trained the data set on open path and evaluated its performance on new data set, that is Kether colon data set, pan new data set, digest part, WSS4 lot dataset. So they have obtained remarkable results if the same dataset is being evaluated on PLIP and versus PLIP. So if we see for Kether colon, so Kether colon have improved far better than PLIP model. Then PAN-NUC, we can see that PLIP model performed better than PLIP model. Similarly, in digest path also, it performed far better than PLIP. Similarly, in this data set also. So the major difference is that PLIP is being based on natural images, and some of the image trained on ImageNet as well. But in case of PLIP, PLIP is being trained on pathology image, and it is very versatile because it has the one of the largest pathological data set uh, to segregate the data. So if we see, the result are 4.2x better than PLIP. In case of in PalmNuke, it's 1.9x better than PLIP. In case of digest part, it is 27.7% better. And in case of this dataset, it is 1.5 times better than that. So further, the authors have evaluated their PLIP model to classify on different kind of organ pathology, and they have used this pan-nuke dataset, and they have obtained quite good result to identify and carrying the pathology of almost all the organs that are present in the body. So they have obtained F1 weighted score, and we see that the purple legend is showing the performance of PLIP for each class for benign and malignant. For this cancer, for bile duct, we can see PLIP is also performing good. Bladder cancer, PLIP is still performing better. Breast cancer, PLIP is performing better. So in all the cases, PLIP has superior performance over PLIP. And major reason is that PLIP is based on natural languages and trained on natural languages, while PLIP is trained on pathological images, which is task specific. So PLIP achieves superior F1 score on 16 out of 19 organs. So we see that its performance is quite good. 7 organ achieve reasonably higher F1 score, which is greater than 80%, while baseline PLIP perform F1 score between 30 to 60%. So we see the previous task is about image recognition. Now, further strengthen the model, we can also use it in supervised fashion instead of using it for zero shot learning or contrastive learning. So in case of supervised learning, PLIP can also use, uh, it will just froze the image encoder and use the projection layer, that is projection layer which is present at the end, and perform a linear classification using the pathology image. So still we see the better performance of PLIP as compared to existing model like CLIP, multi-path, PLIP versus CLIP, and PLIP versus multipath. So we see that on these three data sets, CLIP also performing far better than them. And these model are being trained on these data sets. So their inner working is different than PLIP. And PLIP was fine-tuned on pathology images. Now they have compared their performance, and they have used these F1 score for representation of their work, for representation as an evaluation measure for their model. And on x-axis, they have used the sample rate. So if we see in this data set, they have obtained almost 95% accuracy. PLIP is obtained 95% accuracy on 1% of data. So if we further increase the data to 5%, its accuracy reach to 97%. And if we further increase the data to 10% of ratio of cat and colon data set, so it will further increase as compared to vision transformer. So they have compared their model with vision transformer. Similarly, pan new data set they have used on 1%. Vision transformer is performing 62%, while PLIP for 1% data, it's performing 70%. Same is the case for digest path. We see that 1% of training for vision transformer, it will produce approximately 87%, while on similar sampling rate, we observe that PLIP model performed 93%. So that is a huge performance gain we have seen so far. In this data set, we have also obtained that vision transformer performed 65%, while PLIP model performed 62%. So that is a huge performance gain they have obtained. Compared to end-to-end supervised learning algorithm, vision transformer, PLIP achieved better performance, and the improvement is especially large when the training set size is small. So this is one of the quality of PLIP model is that on smaller sampling size, you can also obtain good result to classify among the classes. So they have proved it with 4 different kind of pathology images along with their own open path dataset. So see only 1% of training, we can observe the result. So another contribution of PLIP is that it can perform text to image retrieval as well. So we can construct a good search engine. We can develop it by passing the text query and text encoder, and it will form the encoding, and then it will retrieve the image which has similar cosine similarity. So they have validated, so they have evaluation data set as well as validation data set. So the validation data set is from November 2022 to January 15. So they have performed some evaluation on it. So these are the total size of the tweets they have obtained for this data set. For Pathpedia, they have obtained these, and for books, they have that. So the evaluation measure to express the performance of text to image retrieval, they have used a recall rate of 50, means that on top 50, they have checked the target or the query image or the query result is lying in top 50 or not. So if the image is retrieved, the target is 100% accurate and it's placed on the first, ranked on the first place. So this is how they have calculated the performance of their retrieval engine. So uh, so they have seen that for the recall rate for the top place position at one, they have obtained approximately 33% of time they have correctly retrieved the same result for the query. But for top three, if the result is in top three, say approximately 67% of result is being obtained for the PLIP model. So let's further see their performance. So these are the dataset for Twitter, Pathpedia, PubMed, and books. And these are number of candidates for top 10 results for PLIP is 27%. For PLIP, it is far less, that is 6%. And overall change versus is 4.5. So PLIP is performing better, 4.5 times better than CLIP. Similarly, for 50, its percentage is 52, while CLIP performance is 12, and it is still 4.1%. Similarly, it's 40% for Pathpedia and 16% for CLIP, 75% for 50, top 50, and 47% for CLIP. So that is basically a most challenging task to perform using image retrieval based on text query. So there might be, the problem is that there might be some anomalies that are present in the text, or the other reason may be the text that is being demanded by the user is not available in the data set. So that might be the another reason for this performance. So PLIP can act as a powerful search engine. So this is one of the demo of their paper for their work. So if you type breast tumor surrounded by fat, it will able to retrieve the image with 30% recall rate, and it is the correct image. And similarly, if we type this query, it will bring the result which is related to this type of cancer. So that is one of the contribution of their work, that PLIP can able to perform a powerful pathology search engine. Then image to image retrieval. So if we pass an test image, it will calculate the image encoding, and then from their existing matrix of cosine similarity, they will identify this image is similar to which index, and then they can able to classify it. So it will help to image search, education purpose, and some other work as well, data cleaning as well. So if we see their work for image to image retrieval, 9 tissue types, we see that it's almost PLIP is performing better than rest of their models. Similarly, in Palm Nuke also for image to image retrieval, it's also performing better than rest of them. And similarly, in this data set also, having 24 staining styles, they can able to identify. So it can able to retrieve the image for tissue type, retrieve the image for organ type, retrieve the image for staining styles. So that is the major contribution of their work. So PLIP can act as a powerful search engine. So here, this is the visual representation of their interface. So here you can just drop the image. It will find the relevant image and also support your work with the tweets that are present to help you to understand and study the work, study the case. There are some other foundation models that are also used for medical diagnosis, and these are BioMedClip, PubMed, BERT, Palm, Med Flamingo. So these are various kind of foundation models that support multi-modular tasks for combining image and pathology image or medical image with their representing task or reports or text. So that is how people are working in these direction. So still there is lack of highly reliable visual foundation model for medical images. So there is a need to further strengthen the work that is being laid by these authors for PLIP and these foundation model. The issue of hallucination or algorithm aversion should be minimized. So this will help to further clean the data and further strengthen the existing model. Medical image are fundamentally different from journal visual images. So these the thing that they have used is that all the models that are appeared on the internet is basically based on natural images, and there is no data that there is no foundation model available for pathology image. So if we use the same kind of images, then it will further strengthen the work. So they say for future researcher, they have suggested to use FLIP to further research in the domain of medical diagnosis. So a visual language foundation model for pathology image using medical tutor. So it supports zero shot learning, transfer learning, text to image retrieval, and image to image retrieval. So basically, we have text, we pass it to text encoder, it will find the text embedding. Then we give the corresponding image to image encoder, it will find the image embedding, and then we'll find the cosine similarity among them. The diagonal have the maximum representation of the same class. So there is a source cosine similarity and target cosine similarity matrix. So this source cosine similarity is based on the provided data set. If your image is not belong to source, still it has the capability to map it to in these class if it belong to these class, and if the image is not belong to any of these class, then the model has the capability to make a separate class for unseen or new rare cases for pathology. So that is how your PLIP model will able to work. So if we summarize their work, so they have produced a versatile data set. Public data annotation with natural language from internet is a tremendous source to advanced pathology AI. And in the field of research, they have introduced zero-shot learning for pathology images, predict new set of data anywhere, anytime. They also support linear probing while keeping the embedding as frozen and taking the output from the linear layer. A preferred model for transfer learning effective way to adapt new coherent. So what they say that if you want to use the model, you can fuse the embedding layer and just use the linear probing to classify your model because it is already trained on large amount of data set. For education, you can query it like a text engine, and it will give you relevant cases to study the pathology and anatomy of the cell organs or stain styles. Then image to image retrieval, you can find similar cases. It will help you for education and to collaborate with one another. So this is the uh, QR code for their code that is available online, and you can use it as a demo to understand their working. So this is the QR code for their collab repository. You can use this repository to run the code, which is very simple, and you can execute how their work will further enhance their work. So their future work is that they are working on a new data set, that is the version 2, and they will going to target 10 million pathology image for representation, and they will also going to work on chat PLIP, which is just like a chat GPT, and you are going to ask, you can either upload the image, pathology image, and you can ask question about that to understand it, to ask about the relevant information. So that is how they are going to work in their future milestones. So that's all about PLIP. I hope my presentation will help you to understand this paper. We will further deep dive into the code of their work to further strengthen our understanding. So thank you so much. Please do watch clip also if you have some kind of confusion in their model. Thank you so much.